Okay, so today we're going to be looking at Strassen's algorithm. Essentially, if you don't know about this, what it is it's slightly more, it's a more efficient way of performing matrix multiplications. The one caveat is for it to be very effective, you have to go recursive. So it's not as widely adopted as one would think, given that if you want to perform matrix multiplications on GPU kernels and whatnot, which we're going to do in the future, then recursion is really not the way to go. All right, so before we get to improving the matrix multiplications, we're going to be performing that matrix multiplication, very bare bones, naive approach. So I'm going to include the stream, and this is just going to be a basic implementation of a matrix multiplication. So how would you call this matrix multiplication function, right? So say you define a buffer of buffer A that has, for instance, I don't know, 1, 6, 3, 4, whatever number you want, and we obviously want to, let's say we want 6, so that would be. All right, so let's say we have a buffer of memory that has this as your input matrix. And essentially what you're gonna multiply it with is gonna be the complement, which is gonna be B, and like this is honestly visually for us, doesn't make a difference in memory. So what we're gonna do here is actually define, and I'm gonna use size T, we're gonna define the dimensions of these matrices. So M, N, and K. And obviously to be able to perform a matrix multiplication, we need the n of the two, or the number of rows of this guy and the number of columns of this guy to be equal, which in this instance we have as 2, and this is 3, and this is 3. Awesome. Okay, so we want to be able to call a function, not main, to be able to call a function called matmul, matrix multiplication. And we want to give this function our A and B. In fact, I'm going to make C buffer here, and C is just going to hold our like values. So I'm just going to pass in C as well, and then it can write over C. So this function is not going to return anything. So what we can do is we should memory set C to 0, and I think we should include C string. Okay, that should work. Okay, we're gonna set this C to all zeros, which we can do by just doing 6 times size of float. Awesome. Okay, so now we're zeros, and the reason that we're doing this is in matrix multiplication, typically you perform, like in the naive approach, you do a lot of like plus equals, so we have to set this to 0. So okay, cool. This is going to be the purpose of our function, and obviously like C++ has absolutely no idea what size this buffer of memory is, so we're going to help it out by actually passing in these variables. So don't cut and paste like I'm doing, but let's see. And we can just get rid of those guys. Awesome. Okay, so we're passing in the buffers of memory, and then we're going to be passing in the size as well. Okay, awesome. So let's define this matrix multiplication function. So it's going to be a void function that takes in as parameters. It's just going to take in a bunch of float arrays. Or float pointers, and the corresponding size. So I'm just gonna cut and paste the values from there. Awesome. Okay. Now what we're gonna do is, again, the naive approach. So if I'm assuming if you're watching this, you're familiar with matrix multiplications, so I'm not gonna dwell too long on that. So we're just gonna have a triple nested for loop, and each nested for loop is just going to have a different function, meaning we're going through M, N, and K. So for that very reason, I'm going to conveniently call these, and I'm using size T because your matrix size might be too large. If your matrix size is too large for some reason, it's good to use size t. Size t is like safe net, I guess. So I'm gonna conveniently name these mi and mi if mi is less than m, and mi plus plus. Okay, awesome. And again, don't cut and paste like I do, but then we're gonna go to ni. If ni is less than n, we're gonna end, and ni plus plus. And again, ki, and k. Okay, awesome. So we already have our buffer of memory that contains the results, which is c. And before I get there, and we're going to be adding these values to some index at c. So before we get there, let's determine what we're going to do. So we're going to multiply a and b together, right? So we're going to be multiplying a and b, or some indices of a and b. So what indices? Again, I'm assuming you're very familiar with matrix multiplication, but if you think about it, we're going to be in the first row or whatever row, and each row has a given length n for a, and in that row we are at index ni, right? Because ni counts where we are within the row, so like the column you are within that row. And for b, pretty similar thing. So we are at a given index ni because that is the n is the row of b, and each row has a length of k, and we're gonna be at ki. So very simple, rudimentary. And if you actually look at this, you'd recognize that c also has the same rows as a, plus it has k instead of for the length, and because we're using k, we're going to use ki. So very basic. This is the naive approach for matrix multiplication, and that should set c. So we're mem setting c, and maybe we can make a function to print. So I'm not going to bore you with printing values, so I'm just going to cut and paste value that I make outside of this video. Okay, so this is very boilerplate and like print statement or print function where you take in the matrix, the row and the column, and essentially you go over each dimension, go over the rows and the columns, and you're just outing the matrix. Like it's the same thing that we did here. Very basic stuff. So I am going to first test this thing. I'm not even going to run this. I'm going to first test it using a to ensure that this is visually, and my computer decided to freeze, this is visually nice. So the size of a are m, and the row of a is m, and the column is n. So we're just gonna run that. So I named this file, I use G++, so you can use whatever compiler. This should work with anything, but some people I know don't prefer that. So but we're gonna compile this and just run it. Awesome. Okay, so you can see, only this expands. You can see that A looks like this, and I obviously did not properly write this, because if I only look at it, I'm saying that it has 3 rows. So this is 2, 3. The way that I wrote it here, I'm saying that it has 3 rows. Okay. Awesome. That looks exactly like what we have right here. And if we write out b and just change out the dimensions, or okay, 1, 6, 3, 4, 5, 6. Awesome. Okay, we're good. And I should probably make these just random values, not e. Okay. Awesome. So we're going to test out our matrix multiplication function first before we even print anything. It doesn't crash. Okay, it printed something for some reason. And we're actually going to print out C. So it has dimensions of M and K. And let's see. Okay, so I actually realized I made a few silly mistakes here. So I had to first initialize this to all 0. And you probably might have seen the cut and paste mistake that I made here. Okay, awesome. So sanity check, let's clear this and run it again. Okay, awesome, it works. Now we're gonna print this, and I'm sure this is some value. In fact, I'm gonna double check if this is correct. Okay, I'm back. It is indeed correct. So awesome. So our matrix multiplication is working. Now, this, again, is the very naive approach. And now what we're going to do is we're going to expand it out a little bit, and we are going to write Strassen's algorithm. So essentially, with Strassen's algorithm, you're just doing some algebraic trick and going from 8 matrix multiplications to 7. And you run the calculation recursively, and I'm just going to show you what it does in a second. So let's collapse all that. And okay, so the other caveat is it's designed so that you can you're supposed to run it on square matrices. Now we can just pad a non-square matrix and just be okay, and that's what people do, and it's pretty normal. However, I am not going to do that today because that is just going to make it longer, and it's beside the point of the video. Okay, awesome. So with that mindset, we're actually going to, instead of using 6 matrices, instead of using 6 elements in this matrix, we're just going to make it a square. So we're going to use 4 by 4 and 16. Okay, so I'm just going to make all of these 4s. Now let's get a base value, and obviously that is incorrect because I am using the wrong size for C. I'm not mem setting it, which, by the way, that goes to show why we need to mem set this. And I mean, I can make this visually nicer to look at, and also not have those empty values at the end, which look disgusting. So I'm just going to cut and paste this, and in all honesty, I'm just going to cut and paste it here too, and just pick some random values to be different, like 9 or something, and 2. Okay, cool. Now we have a value that we're shooting to get with our new Strassen's algorithm. Okay, so let us begin. We're first gonna define the function, which if I can spell, it's gonna take in, I'm just gonna make it a void function as before, and it's gonna take in same thing that matrix multiplication was taking in, but in addition to that, and I'll show you why, we're gonna take in a few more values, and the values we're gonna be taking in are let me show you why we need it before we begin. Okay, so you're taking in this float pointer, right? Like 3 buffers of memory. Now we have a contiguous buffer of memory, and if you have something like this, and you want to run Strassen's algorithm on it, and like say you want to run it from there to there, or you want to run it on the entire thing, you have to break it up into 4 chunks, right? So it works by essentially, I encourage you to look this up because this is beside the point of the video, but it works by breaking up each matrix into sub-matrices, and then going on until you, well, I guess it's part of the video, going on down the recursive chain until you reach the base case of like a 2 by 2 matrix. So like this chunk would be processed. Aside from this, you're gonna have to be breaking it up. Now we have a buffer of memory, right? Like visually this looks like, oh yeah, like you take 1, 6, 4, 5, but this is what C++ is. Like it has absolutely no idea how to index this out. So that the way around this is, what you're going to be doing is you're going to be passing in, or what we're going to be doing is we're going to be passing in the offset. So you say, hey, go to 1, 6, and then an offset of this value and go here. And what's the offset? You just go to like from here to like whatever this is plus the row. So the row length. So 1, 2, 3, 4. So you're going to say here and then go 4. And then you're going to come down here. And then after that, you just add 1, because you know at that point you have a 2 by 2 matrix. So essentially that's what we're going to be doing. Okay, let's begin with the base case. So the base case is if our chunk, right, the level that we're on right now is a 2 by 2 matrix. So how do we define that? How do I know the dimensions? Obviously M is like the size of the entire buffer. So that is when we're going to use our additional parameters, right? So I'm just gonna, to be honest with you, I'm just gonna call this mi, ni, and these are gonna be the local variables, like the local, what is the size of this tiny little chunk, right? And the idea is mi is gonna be equal to 2, and ni is equal to 2, and ki is gonna be equal to 2. Awesome. Okay. So now, if we hit this condition, that's our base case, and let us first see, like I want to visually see that I am actually indexing, I am actually getting this, this block out and not gibberish, okay? So, or not other junk. Okay, so I have, yeah, okay. So we're gonna do C out, and we're gonna start with, let's say A. Say we just care about A for now, and we're gonna say A is, like we said, this plus the row, right? So we're gonna go like one row. So whatever index we are at for A, plus one row. So what index are we at for A? We have no idea. So those are additional parameters that we're gonna be passing in. So those parameters are gonna be the offset parameters, okay? So I'm going to call conveniently again, call these offset of A. I'm just gonna call it off A, or not off A, sorry, offset of M, and offset of N, and offset of K. Because like we don't need, N is repeating, we don't need to do repeated work. Okay, so we have these like offsets, right? So now what we're gonna do is, hey, I am at an offset of M from A, and then we know that with each offset, we're going to be jumping an n value, because that is the length of the, similar thing to what we were doing here. That is the length of one row, right, for A. Now, after this, what we're going to do is we're going to add the offset of n, right? So you might notice this looks surprisingly similar to this right here. Offset of M, offset of A, offset of M is this, n plus ni. So these are just like ni, yeah, I know, like I mix up the labels, but essentially these are ni and mi, right? So very similar, nothing super new. And the next thing we're gonna print is, because keep in mind we have a 2x2 matrix, so the next one is gonna be exactly the same thing, but we're gonna be shifted one to the right, right? So we can do that, and I'm just gonna add a separator here so that the numbers are actually separated. I'm gonna put a comma right there, and maybe I'm not gonna use end line because someone might be mad. And let's see. Now the second row is just gonna be like same idea as before. We're just gonna be, instead of n, we're gonna be one row down. So I'm just gonna make it abundantly clear by writing it this way. And similar thing right here, instead of +1, or visually I think it's better to do here. All right, so we should, after running this, we should be printing this guy. Now keep in mind, this is the base case. We have not even defined anything yet. Like we're not going recursive yet, not yet. So essentially what I'm gonna do right now is, or what we're gonna do right now is we're gonna be like defining the recursive tree, right? So if, well, this would be the else case, but let's see. So we're just handling two by two like square matrices right now, so we don't need to worry about like having a case of one. So I'm just gonna do else, but you should be able to. In fact, I think I'm just gonna write it out. Else if mi is greater than 2, ni is greater than 2, and ki is greater than 2, or rather not greater than, okay, it's supposed to be or. And the else case is you have 1, right? A row of ones, or sorry, like one element. So that's what I didn't want to handle. Anyway, it's better to do it now. And the idea is we're just going to be calling the same algorithm. We're just going to be saying Strassens, and then we're going to be passing in functions, right? So we're going to pass in A, or parameters. So we're going to be passing A, B, C, M is not going to change, N is not going to change, K is not going to change. Now MI, that's going to change. What MI is going to be is it's going to be the same thing divided by 2. Because keep in mind, if we have a 4x4 matrix and we want to isolate this guy from our matrix, then it's not working. Then we have to divide the row by 2, and we have to divide the column by 2, right? So that's why we're going to be dividing by 2, and dividing each of these by 2. So the other thing that changed right now is the offset. So we're just trying to print the very first value. So I'm going to set the offset to offset plus 0 because we're going to be right here. And this would also be offset of 0. Okay. So I have not run this before. I'm just gonna see if it works. And obviously I made a mistake because I didn't pass in any parameters to this. So I'm just gonna cut and paste this. And instead of this, we're just gonna be in the beginning, we're just gonna be at the same values as the size of the matrix. And I guess I can just do that. Awesome. Okay, 1, 6, 4, 4, 5. Perfect. That is what we expect. Now, obviously, we're going to start with this. We're not going to implement Strassen's right away. We're just going to be doing regular matrix multiplication using the recursive approach, of course. So to do that, there's going to be a lot of boilerplate stuff, and I'm just going to hash that out. And what we're going to do is let's actually think about this, right? How many positions can we be in, right? We can be here 1, 2, 3, 4, right? And same exact thing for for the other matrix, right? So we're gonna have to be calling this 8 times. So that's 1, 2, 3, 4, 5, 6, 7, 8. So what's gonna change? For A, obviously we can only be in 4 different locations, right? So for A, then what's gonna change is just the offset. I'll tell you right away. For A, we're just gonna be in 1, 2, 3, and 4 locations, right? So we can just write this out conveniently by saying we're in like offset of 0 for the row and offset of 0 for, because offset of 0 for M, and okay, the way that I wrote it out might make it look confusing, but so 1, 2, 3, 4, 5, 6, 7, 8. Yeah. Okay. So in 2 of the 8 cases, we're going to be, for A, we're going to be on the first row. So it's going to be an offset of 0 for the row. 1, 2, for 2 of the cases, right? And the same thing applies for the cases of C, right? So that's what I'm hashing down. So say these are the cases of A. So we're going to be on the first row and on the second row. Right? So in the first row, we're going to have an offset of, and I'm going to bring back the hashed out values, but on the first row, we're going to be at an offset of 0 in the column, and then we're going to be at an offset of ni over 2, because we're pushing ni over 2 to the right. So we're going to be an offset of ni over 2. And then what's going to happen is we're going to be on the second row, which is going to be mi over 2 plus mi over 2, and then ni would be 0. And then lastly, we're going to be at mi over 2 and then ni over 2. See, so we're handling the case of A. So let's do the same thing, bring back C. So that's why I had these values here. And you can just pause and look at these values and just mentally confirm for yourself that that it all makes sense. So yeah, and let's just populate them. At this point, you can just honestly turn your brain off and just visually, I think this looks nicer. Let's make it alternate. So at this point, you can just turn off your brain and just fill these in. So again, I want it to alternate for some reason, so I'm going to be doing this. Okay, awesome. 0, 0, 0, 0, M1, okay. Alternate. Okay, so now that brings us to the wonderful case of the wonderful case of K. So K defines the column of, K defines the column of both the matrix B and C. So again, you can just think of it like logically like we did earlier, and you know it's going to be a stride of Ki over 2. So I'm just going to fill these in right now because this doesn't really require that much thought. Okay, so now we're jumping to the right positions for all matrices, hopefully. And what we can do is we can conveniently write this again, and I'll just add a C out of times for matrix multiplication, and yeah, these should be B's, right? So B, 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 and obviously we're supposed to have the right offset, because with B we're working with N and K, N and K, offset of K, offset of K, offset of K plus 1, offset of K, that would be K. Okay. Awesome, that should show us stuff. Okay, actually I should probably add a break in between each recursive call. Otherwise we won't be able to tell what is what. And okay. All right, let's expand that out. Only that works. Okay. So we are getting something that does not look very nice, because I don't have an end line here. Okay, that was weird. So we are getting, we're multiplying 1, 6, 4, 5, and let's just see if it's indexing it out right. 1, 6, 4, 5, and 3, 4, 6, 4, 3, 4, 6, 4, and 1, 6, 4, 5. Maybe I should probably rename that to be able to catch it. So 4, 6, 9, 4, 6, 4, 9 is what we expect, and 4, 6, 4, 9. Okay, awesome. So, and you can just pause and check that B is correct too. That looks correct to me. Okay, so now we are getting in and we're heading our recursive call. So we don't need this C out anymore. Now we can actually make our matrix multiplication. So with matrix multiplication, this thing is annoying. With matrix multiplication, we're just going to calculate, like you have a 2 by 2 matrix, right? You're going to have like an A11, and you're going to have A12 and A21 and A22, right? So similar thing for B, for matrix B. So you're going to be having the exact same thing for B. And for C, again, same exact thing. You're going to be having C, C, and C, right? So we're trying to use these values to populate C. That's essentially what we're doing. Now, what is A11? Well, it's going to be similar to, maybe I should not have deleted that so quickly. It's going to be similar to the C out versions that we had, right? So A11 is just going to be this. So it's just going to be that, and move one along there. Okay, so I just cut and paste these values here. So now we can get rid of this. Now what we're going to do is we're going to populate C, right? So C11 is just going to be multiplication of A11 times B11 plus A12 plus B21, right? And C2 is just going to, you already know how to do matrix multiplication, so I'm not going to bother with this. I'm going to, okay, cool. So we have these values. Now you might ask the question, where in C are we going to put this, right? So we know how to index A and B, but where in C are we going to put this? My answer to you would be here. So similar to how we index C, we're just going to be indexing C again. Like in a very, in fact, I'm going to cut and paste this just to show you how similar it's going to be. So we said Mi is going to be the offset of M, right? There you go. And then multiplied by K, and then Ki is going to be offset of K. So that is literally where we put C11. And oops. So we can just populate the rest like we did with the others. Okay, I just went and populated that. And essentially we're going to assign this value to C11. Now you might notice that there's absolutely no need to have a C11 variable. So we can just do this. And be absolutely okay. Okay, so we're going to be calling this same value multiple times. For C, so instead of equals, we should be doing plus equals. Okay, so that should populate our C value and call Strassens on the right values. And this should theoretically work. Let's see if we crash. We don't crash, good. So let's see if we're in the right value. So you might notice I'm actually writing over C twice. So yeah, so that's just the Strassen's value, and this is the matrix multiplication value. You see they are the exact same. Or no, not Strassen's, the recursive and the non-recursive. So they're the exact same. Now we can very gladly apply our Strassen's algorithm. Now, what we're gonna do is, I encourage you to pause this video and go and see what the Strassen's values are, because this is getting too long. I'm just gonna cut and paste the actual values that I pre-wrote. Essentially, Strassen's is doing an algebraic trick and trying to reduce the number of multiplications that we're performing for each like 2 by 2 matrix multiplication. So if you count this, you have 1, 2, 3, 4, 5, 6, 7 multiplications. Initially, we had how many? If you count it, it's 1, 2, 3, 4, 5, 6, 7, 8. So we're going down 1. Now, like, there's other videos and like articles talking about like how this 1 matters when you're going recursive. Just watch that, honestly. Here, I'm just gonna show you how it matters in a very practical sense. So I'm just gonna populate these again using predefined values. Okay, awesome. So this is what it's gonna be, what it's gonna look like, right? So, and again, like I'm defining so many variables here. If we call this like a bazillion times, that might not be optimal, you know. But we're not gonna be dealing with that right now. So this is our Strassen's algorithm, and let's actually run it and see if it is gonna work out properly. So number 1, does it crash? No, it doesn't. Number 2, does it give the right value? Yes, it definitely does. Okay, now you might not be able to tell if this is more efficient or not. Now we can just add a timer. So I'm just gonna hashtag include chrono, and the timer that I'm going to define, is just going to be a basic timer that upon instantiation of the class, it's gonna create the timer, and then upon destruction, it's start the timer, and upon destruction, it's just gonna print out the time. Okay, so for the sake of time, I'm just gonna populate the timer, and you can let's talk about this, right? So upon instantiation, we say that m start point, which is defined here, it's just a high resolution clock. We start the start point, and right upon destruction, what we're gonna do is we're gonna say, hey, the endpoint is right now, and calculate the duration by subtracting the end from the start, and use microseconds. We can go nanoseconds, but I don't think that's necessary here. And we're just gonna define, we're just gonna multiply by, this is, so, because we're in microseconds right now. So the way we call this timer is just gonna be very simple. Right before we do our, two options, right? Right before we do our multiplication, and we're gonna call it, and upon destruction, it's gonna print out the value, as you can see here. Okay, let's actually test out this timer, and it says 1 e minus 6, because this is going to be, obviously, it's going to be very, very fast. And let's test it with this. Yeah, because again, like we're just doing such a simple matrix multiplication. Now, let's strain it out, right? So I have tried this before, so I'm not going to bother with it. The highest amount that we can put in a stack frame is 256 by 256, so I'm just going to do that without heap allocating. 26 and 256 by, should probably make a variable for this, but there you go. All right, so, and the rest, like in this case, the rest are just going to be zeros or whatever gibberish. We don't care about the actual values. All we care about is we are timing how much it takes that matrix multiplication. Okay, let's run this. Now it took that however many seconds that was, and we're gonna run, actually let's run this, because typically, like if you're timing, you should do it multiple times. And obviously I'm not sure if, yeah, let's do that, and it seems fairly consistent. Let's do Strassens, and you can see there's an improvement. Whether that's a significant amount of improvement or not, I'll leave it up to you, but there is indeed an improvement in the algorithm, and it's pretty repeatable. Okay, so another thing to note is if you're running this under release, your compiler is going to do some optimization, and in some instances, the naive approach might be faster. And another important thing to note is, actually, I'm going to show you this first because this is interesting. You see this as hitting, this if statement is being hit before anything, right? So oftentimes, what's going to occur is this condition is going to occur. So let's do this. Let's run this a few times. And then after we're happy with that, we're going to move this condition upwards. And then we're going to say else if that, and then else nothing, because that never gets executed. And let's run this again. Now, this is very, or should not have cleared that. It's a very small change, but you do see some level of improvement when this statement is being hit first. So just an optimization note. Now, if you're unfamiliar with OpenMP and OpenMP parallelization, it's basically using multi-threading to collapse for loops. So because I do not know the... Okay, so yeah, you're just going to add this statement right for your for loops and just make sure that there is no, like, f is equal to 2, like no definition like that in between. So we're going to be collapsing 3 loops. So this just says parallel, collapse 3, and then it's going to run in static mode. So you're not like, you don't have anything that's like actively changing within here. Now, you do, but and running OpenMP with the plus equal sign does lead to data erases. There's ways to get around this. You can use atomic. That is not the point of this. I'm just trying to show you how to optimize your naive using OpenMP. So you're just going to add this statement before you as you compile the compiler statement f OpenMP. And you hit that, and it makes no difference because we are actually in Strassen mode. Let's do map move, and as you can see, the time significantly collapses, no pun intended, when you're using that. And if I just remove the flag for OpenMP, you're gonna see the increase. So essentially, it's like making this like one flat loop and then multi-threading it over it. And we can talk more about this in a future video and how to use GPU kernels and all that fun stuff. So for now, I'm just going to leave it here. I'm going to add the code in GitHub. I'm going to put the link in the description below. Thank you for watching this long video.